Okay, so welcome to the Tutte Colloquia, and we are very happy to have Jane Ye here as the speaker of this week. So Jane obtained his PhD in 1990 from Dalhousie University, and since 1992, she has been working as professor of mathematics in University of Victoria. So Jane works on non-smooth optimization and variational analysis. And today she's going to talk about bilevel programming problems. So welcome, Jane, and the stage is yours.
Thank you, Jane, for the introduction. And thank you for inviting me to give a seminar here in University of Waterloo. Yeah. So this is a joint work with my former PhD student, Quang Bai, and my former postdoc and another PhD, and they are all now in Hong Kong and China. And today I'm going to talk about solving bilevel programming problems, because this is my favorite topic, and I've been working since in these topics since 1992. Since 1990. Okay, so first I will give an introduction to bilevel programs, and I'll review various approaches for bilevel programs. Then I will mainly talk about new optimality conditions called directional optimality conditions, and a new algorithm called difference of convex algorithms. Okay. So first, the bilevel program start from economics. It was first introduced by Sternberger, and so it's a kind of game. Okay, so you have leader follow a game, and then this is actually a very important model in economics. Is a very basic. So, for example, the classical principal agent model, also called moral hazard problem in economics. This is a situation where you have a principal and agent, so like boss and employee, right? And the boss can only observe the outcome of the employee, and you cannot control, you cannot see how the employee is working, right? How hard the employee works, you cannot control that. So the boss will design a contract. So the contract, for example, a wage, right? Wage scheme, in order to maximize the utility. Usually there's some stochastic probability involved. So expected utility, and subject to the employee optimizing, they're always optimizing their own objective. Okay, so this is an important model, and in economics, so a Nobel Prize has been awarded twice for study of this very basic problem. And for optimization community, we know that the first time the bilevel program was introduced was in 1973. Then in machine learning in 2006 in this paper. And then in this big data era, machine learning, in machine learning, people talk about usually have this kind of optimization problem where you minimize some kind of loss function f, and then here you add a regularization term, like a penalty term. Okay, so here usually lambda, the penalty parameters are fixed, and then you try to run this training problem to solve theta. But actually, this lambda, how do you choose lambda are very important, right? And how do we choose the lambda? So this lambda is called hyperparameters. So actually, you can find some objective function and then formulate the problem as a bilevel problem. Here, lambda, the hyperparameter, is upper level variable, and theta is the lower level variable. So you can find both lambda and theta at once. Okay, so I'll use a simple example to explain this idea. Okay, so remember in a linear regression, right? We're assuming you have some x and y has some linear relationship, and you try to estimate theta. So here x is independent variable and y is the response. And in the classical linear regression model, you will take the n sample, n observations, n should be greater, much larger than this, the numbers of the independent variable p. Okay, and then you can use linear regression to find this estimator. This is square estimator. Okay, so but in the big data era, the numbers of independent variables may bigger than the numbers of samples. And then in this case, the classical linear regression problem is year post. And there are some irrelevant variables included in the fitting model. And that's why P is very large. And because some variables are irrelevant. Okay, and I believe this Robert Tipashani is your alumni, right? He obtained undergraduate degree from Waterloo. He introduced this so-called lasso. So given the lambda, so it's like a penalty parameter, and lasso problem is sort of like a penalty least square method. You minimize this mean square error plus this penalty. So if lambda is bigger, then the solution, the optimal solution, will be sparser, right? It means there are more zeros in the component in the optimal solution. But we choose this. We select this data from sampling, right? So there is a true model here. So how many true? How sparse is this true optimal solution? It's already there. Okay, so you want to know how to choose this lambda so that the model is correct. Okay, if you have a lot of some, because we have already not a lot of samples. The number of samples is less equal to the numbers of independent variables. So we cannot afford to leave out some observations, test the results, right? So this is a popular method in statistics to use the existing the available data set to test. So given a data set, right, you randomly split this data set into k disjoint blocks with approximately equal size, right? So this Okay, so k is says 3 or 5 or 10. So for each k, for each one, we leave out one part. So omega k as leave out as a test set, and then use the rest of k minus 1 blocks as a training set, and then you compute the fitted value theta k. Okay, so then use this theta k, use the test set to test how good this fitted value perform. So you calculate the mean square error on the observation on the test set, and then because we calculate from 1 to k, so we take the average. So this is the so-called cross validation error. Then repeat step 2 or 3 for various values or lambda. So ideally, you want to find lambda stars that minimize the cross validation error, and in the meantime, you get the best fitted value. Okay, but there are infinitely many lambda, and then for each lambda you solve a problem, get the fitted value theta. There are infinitely many of them. How do you choose these two values? So in statistics, either a grid search or path following algorithm is performed on lambda value to select the value of lambda, for which then so you can just try to find the value so that the cross validation error is, well, it's almost smallest. But these approaches do not scale well and have a lot of limitations. In particular, if you have more than one penalty parameters. But in essence, the cross validation in lasso is the following bilevel program. So here, lambda is the upper level variable. Fixed lambda for each k, you solve this lower level problem. Okay, and then you want to find the lambda, and lambda star. Okay, and the corresponding theta star, so that this cross validation error is minimized. So this is exactly the bilevel problem. Okay, did I miss the first page on the introduction of the problem? I'm not sure if did I sorry. Did I do this page? I may have missed this one, right? Somehow. Okay. So the bilevel program is this, you minimize the capital fxy. Okay, so here y is in the solution set of the lower level problem. Okay, so we assume you can have some upper level constraints, but these are, we can just upper level constraint, you can have equality, inequality constraints, right? So we just omit it. Okay, so this is the bilevel program. Did I do this part? No, I think somehow yeah, okay, I don't know what happened. Okay, so then for each x, the lower level problem, suppose for each x, the lower level problem has a unique solution, right? Then you can submit this function into the upper level. Then the bilevel program is basically becomes a one level optimization. Okay, but in order to solve problem, for example, if you use a gradient method, you need this yx to be a function, but and also it need to be smooth. So if you have all these, you can solve this function, then you can solve, but that's not easy. And if the lower level has multiple solutions, then there are two versions of the bilevel program. One is optimistic, another one is pessimistic. So one is optimistic is the one we want to discuss, okay? And pessimistic is the, here is the maximum. So minimize the worst error. So in this talk we deal with the optimistic case. Oh, yeah, so that's 2 page. Skip the 2 page. Okay, so yeah. Okay, so maybe, yeah. So here we have okay, so you see this is a lambda is a upper level variable, and for each lambda you solve theta, right, as a lower level solution. Okay, and then so here, okay, so now I will review some approaches for solving bilevel programs. So if for each x the lower level problem is convex, and everything, all the functions are smooth, and the constraint qualification such as the later condition holds, then you can use the optimality condition, the so-called KKT condition, right? So it means that there exists some multiplier lambda such that this is the gradient of the, this means the gradient Lagrange equals 0, right? And this holds at the solution, low level solution. Okay, and then it is popular to solve this so-called mathematical program with complementarity or equilibrium constraints. Okay, so here you minimize over the x, y, and the Lagrange multiplier. And this is the KKT condition. But there are two issues involving using this approach. Okay, so the first approach is the first issue is that the condition, this is the complementary slackness condition. Okay, so this is a complementarity constraint. So if we treat it as the equality or inequality constraint, it means lambda is greater or equal 0, and G is less equal 0, and inner product equals 0. Then the usual constraint qualification, such as Montgomery-Formowitz constraint qualification, will never hold. And we know that MFCQ is very important, right? Because if it doesn't hold, then the local minimizer may not satisfy the KKT necessary optimality condition. And the numerical algorithm may not be stable. Okay, so this is one issue. The issue B is that if the lower level has multiple multipliers, then a local solution of MPCC may not recover a local solution of original problem. So there are these are two issues. And the most important issue is that this approach only apply to the case where the lower level problem is convex, right? So we look at the case, what happens if you apply the first order approach for the bilevel problem where the lower level is not convex? Let's get an idea what happened here. Suppose we consider a very simple case, right? We just assume no lower level constraint. So we just have upper level objective, lower level objective, that's it, no constraint. So the first order approach is replace the lower level problem by its first order condition. So we take the gradient, set it to 0. Gradient respect to y, set it to 0. So because of the non-convexity, right, the feasible region for this problem is larger because this will include not just a minimizer, also maximizer or inflection points. So these are just contain stationary point. While this one, you need to have all the global solutions. And okay, so another question is, can we use this problem to get some candidates for the bilevel problem, the solution of the bilevel problem? Well, for non-convex optimization problems, we only happy if we can find stationary point, right? It's difficult to find a global or even local minimizers. So the question is, if we solve this problem, SP, okay, can we always find a solution, optimal solution of the original bilevel problem? So here we look at the example. It's from Malie. Okay. So if you look at this objective, lower level objective, it's a non-convex function. Given x is a non-convex function, and then you can set a directive, okay, to 0 of this lower level objective, right? And then since everything is smooth, you can just and it's easy to find the relationship between x and y. So you can solve x, and then get this. Then we get this equation, and then we can. Okay, we can make a graph. So this blue line is contains the stationary points. Okay, so here, for example, you have x, you take a value x equal to 1, right? Then you go here, you get these 3 points, right? Are all stationary point. And then among the stationary point, you can solve the lower level problem and get this true solution. So these red part are the true solution. So the these red lines, the union of this red line, okay, is the true feasible region of the bilevel program. But if we use the first order condition, you will get this smooth blue curve, which is bigger, right? Has a bigger region. So now, if we use since the objective is just quadratic, right? So the contour is just a circle. It's actually a circle. So this point is if you find the minimum for SP, right? First first order condition, the feasible region is the blue line, so this is the minimum. But the minimum for true bilevel is at this point, because the feasible region is the red part, right? And then you make this contour bigger and bigger, and this is the first time touch the feasible region. So the optimal solution of two problems are not the same. And more than that, even if you look at the stationary point, which is this one, okay, you can easy to tell there are stationary points, because if a point is a stationary point, then the gradient of the objective should be parallel to gradient of the constraint. And these 3 points have this kind of property. But the true optimal solution is not a stationary point. It's not a stationary point because the tangent are not parallel. Okay, so there is a big problem if we use first order approach when the lower level problem is non-convex, because you may totally miss the optimal solution of the bilevel program. Okay, so how do we solve this problem? Can use the value function approach. So here, instead of original problem, says that y is a solution of lower level problem. So now we say that let this Vx be the optimal value of the lower level, and say that the objective of the lower level must be actually this equal. This means equal because it's always greater or equal 0. So then there's another way to say to write a bilevel program using the value function. Okay, so now even if we assume all functions like capital F, little f, and constraint g are continuously differentiable, this function may not be differentiable, and it's and even worse, it's an implicit function. Right? How do you solve the value? So that's the first difficulty. The first difficulty is that value function is in general not even continuous. It's usually ellipsis continuous under relatively minor condition, but not differentiable. And it is implicitly defined. So how do you solve this, or even write a optimality condition for this kind of problem? Okay, so that's the second difficulty. It is a non-smooth optimization problem. And the usual constraint qualification, such as here you have to talk about non-smooth MFCQ. Right? That Montgomery formalised constraint qualification does not hold. And okay, and even if we have all these, okay, so even, but if you can make sure the value function is ellipsis continuous, the resulting KKT condition can be too strong. Okay, so why is that too strong? We can look at this. Okay, so first, before we look at some reasons, here first, maybe not everyone is familiar with non-smooth analysis or non-smooth optimization. So here, assume everything, all problem functions are smooth, but even that this function is still non-smooth, right? Okay, and then we need some replacement for gradient. Okay, so there are some replacement for gradient. Okay, so say this is a convex subdifferential. So for example, think about the typical non-smooth function, like absolute value function, right? We know that at the origin, the non-smooth, the function is not differentiable. But at the origin, you can always support by any hyperplane with slope from -1 to 1. Okay, so that's V. V is the slope of the hyperplane supporting the function at the point x bar. So this convex subdifferential. Okay, but if a function is non-smooth, is non-convex, then this kind of supporting hyperplane may be empty, right? So then you can add this little o in the right hand side and consider the so-called regular subdifferential. Okay, but again, this may be too small, maybe empty, still empty. Then you can just consider this so-called limiting of Montecovici subdifferential. So that is, you take the sequence xk converging to x bar, and the function phi converges phi x bar, and take this kind of element in the regular subdifferential, and then collect all the limiting points. Okay, then this kind of subdifferential is more robust. Okay, but it's not convex. So sometimes we need to use a convex Hall. Okay, so these when the function is convex, all these are the same. Okay, they're all the same. And so if not continuous, if the function is not continuously differentiable, then these sets may be non-singleton, the set. Okay, so now okay, so we can now go back to the value function reformulation, right? So this is a reformulation of the original bilevel program. And then remember everything else, all these are smooth, so only non-smooth term is the value function, right? And then you can write down, suppose you have constraint qualification, then what is the KKT condition? So it's basically here you need to use, because this is a sub-differential, so maybe a set not singleton. So all you need to do is replace equality by inclusion. Okay, and then this is the Lagrangian, right? Because you have these two constraints. So here's mu is the multiplier for this, and lambda is multiplied for this, right? So basically this is just a Lagrangian, but KKT condition, but with limiting sub-differential. Okay, so here you may wonder why I do not take the lambda, the negative sign out. But for limiting sub-differential, it turned out that this is not equal. You cannot take it out. But so that's why we should use the Clark sub-differential. So Clark sub-differential is convex of this. So of course it is bigger. And because it's convex, you can exchange it. So you can take the negative one out. So it has better calculus. Okay. So how do we use? How do we find this Clark sub-differential of the value function? We call this value function is implicit, right? So we cannot find expression, but luckily we can find the expression for the Clark sub-differential. Okay, so it is basically under some minor assumptions. You can find it's not equal, but it is included in this set. So here is just basically, if you use Lagrangian function, is the gradient of the Lagrangian function respect to x. And here y is, oh, this is typo. This should be y, not y bar. Here also y. So y is any solution for the lower level problem. And the lambda here is a KKT multiplier. So I here use the notation KT. Okay, so it's a KKT multiplier for problem Px star x bar at y. Okay, so now if you put this, because it is bigger set, so 0 is still in this, right? So you can just write down KKT condition, and everything is in terms of problem data. There is no unknown here. Okay. So now the question is, can this kind of KKT condition hold? We know the KKT condition always needs some constraint qualification. It does not always hold. So we'll see how strong is this KKT condition. Again, we can look at the simple case where the lower level is unconstrained. Okay, so in this case, you write, we can again use value function to rewrite the problem, right? Instead of saying y is a solution of the lower level, is a minimize of f, we can say the fxy is less equal to its minimum value. So, okay, so now you write the KKT condition. Actually, the first one is the inclusion because the non-smoothness, right? And the mu is a multiplier. And the second one, because gradient of little f respect to y is equal to 0, because it's optimal, right? So it's the gradient equals 0. So then we have if we take the gradient respect to y, we get this. But this condition is very strong. So at least it does not hold for Malise problem, because in Malise problem, f is this function. And then the gradient respect to y is just 2 times y bar minus 1. And y bar, the optimal solution is less than 1. So this is a negative number. So it cannot be equal to 0. Okay, so this is an observation, right? This observation tells us this KKT condition by using value function approach is kind of strong. So we in order to cope with this difficulty of the first order approach and value function approach, we propose to combine the two approaches together. So this is the value function constraint, and this is the KKT condition. So we combine the both, right? So you can look at the case when the lower level is unconstrained to get the idea. Now, then it's very simple. We only have a upper level, capital F, and the lower level objective, right? And because now we will have a lower level, we have a constraint gradient of y equal of F equals 0. So we have the second order term, okay? And so we will have now more flexibility to choose the multiplier beta. And now remember that this part is for the Malise problem, this part is the negative number. It cannot be equal to 0. But now if we use the combined approach, we also have this term due to the first order constraint. And so this term is positive, right? Positive. And so this condition holds for beta equal to this number. So the usual constraint for qualification does not hold for any of the reformulations. So we'll use the following. Okay, so now I will discuss the new optimality condition. The first one, the so-called directional optimality condition. So because the usual constraint qualification does not hold, okay, so we can look at the value function approach, right? And this, if we consider use the first joint condition, we will say that there exists some multiplier, non-zero multiplier, such that this holds. Okay. If this set, the Clark subdifferential, can be replaced by a smaller set, then the condition is sharper, and then the constraint qualification is weaker. Okay, so this is a motivation to consider directional optimality condition. So what is the directional optimality condition? So first, in the limiting subdifferential, remember we take the sequence converges to X bar. Now you only take the sequence converges X bar in direction D. Then we have now a directional limiting subdifferential. For example, if you consider the absolute value function, then the limiting subdifferential is in the interval -1 to 1. But if you just go from the right, you get 1. From the left is -1. So it is much smaller. Okay, so this is a directional optimality condition proposed by Freire. Okay, so the only difference is replaced by the limiting subdifferential by directional, the smaller one, and also this complementary slackness condition has you have a complementary slackness condition in terms of the directional directive. Okay, so then this is weaker. The constraint qualification is weaker and is some kind of directional version of MFCQ. Okay, so we know that MFCQ will never hold for the bilevel program, no matter you use which reformulation you use. And now we show that if the value function is directionally differentiable, then even the weaker condition, the directional MFCQ fails. The fails. Okay. So then, because directional MFCQ fails, we will try to use a calmness type of condition. Okay. So first, we can, if we have a direction D, then the neighborhood unit, the neighborhood ball can be reduced to a section. So here is the D, right, with some delta. You can just restrict the ball on this. Just look at this part. Just use this part. So this is the so-called directional neighborhood for the origin. Okay. So then, because the direction MCQ is too strong, we introduce a direction version of calmness condition. So the calmness condition, Clark calmness condition, is a kind of idea that is suppose the X bar solve the problem P. We say a problem is calm at X bar if X bar also solve a penalty problem where the constraint is penalized into objective. Okay, and in the original Clark calmness condition, this is the unit ball. Here we can reduce it to the smaller neighborhood, the directional neighborhood. Okay, so it is weaker than if the direction is not equal to 0, then it is weaker than the Clark calmness. So then with this weaker condition, we can have the weaker optimality condition for the value function reformulation. So here, this is the non-directional Clark subdifferential is replaced by the smaller Clark subdifferential. Okay, so now we'll talk about a new algorithm. It's called difference of convex algorithm. So the motivation is that most functions can be represented as a difference of convex functions. For example, lower C2 functions, which is a maximum of some C2 functions, and C1 plus functions are all DC functions. And the class of DC function is closed under many operations. If the lower level problem is completely convex, which means convex in both variables, X and Y, then the value function is convex. And so this constraint becomes a DC constraint because F we assume is convex, and then Vx now is convex. So this is a difference of convex function. And we can then use the difference of convex algorithms. But we need to study two issues. Because in the difference of convex algorithms, you need all functions to be convex and Lipschitz continuous. Okay, and so we need to find conditions. And also we need some kind of constraint qualification. For example, we need a so-called extended MFCQ. Okay, so we will study this difference of convex bilevel program. So objective function now is the difference of two convex functions. And this F is completely convex, and G is also completely convex. And we assume this, we make some assumption, okay, so that we have the, okay, so we have these assumptions. And so you may think that this is, there are a lot of restrictions, but for this formulation, but according to this paper, if the lower level objective is in this form, which may not be a completely convex, you can always reformulate, do some reformulation so that you have a problem that has a completely convex objective. Okay, so this it is broader than it looked like. Okay, and we also need some assumption. We will assume the solution is non-empty, and then we also assume this is feasible region is non-empty, and the lower level objective is bounded below on the feasible region. Okay, and there's also this this assumption because we are in using non-smooth subdifferential, right? So for convex functions, just a convex subdifferential. Normally, we may not have equality, right? If they are differentiable, of course it is equal, but not differentiable, we will need this formula to be true. So we call it partial directed formula. For example, if the function is separable or separable in variable x and y, okay, then this is true. Or if C1 respect to either x and y, okay. And also, normally in bilevel problems, all functions are assumed to be C1, like what I did in the first part, right? Talking about optimality condition. Here, we in the convex in the DC program, DC bilevel program, we do not assume convexity. Do not assume differentiability. So maybe go up here. So this is all x and y are non-empty closed convex sets, and this G are convex but allowed to be non-differentiable. And this function, all these functions are convex. Okay, so they are allowed to be non-differentiable. Okay, so here, so this so for machine learning example, this is true. Okay, see, this function, objective function is C1 respect to either x or y. Okay, so we can now reformulate the lasso as a bilevel program with a completely convex lower level program. Okay, so remember we have a lasso problem, right, as a cross validation problem, as bilevel problem. And because you have lambda times one norm of theta, it does not look like a completely convex function. But if we use a transformation, divide the lower level by lambda, then we have this, and this function is convex, completely convex. So this lower level is completely convex bilevel program. And then, okay, so another application is to support vector classification. So here, you want to separate, you have two kinds of points. So maybe quickly, you have two kinds of points, blue dot and triangle, right? and you try to separate these two kinds of points. So using a hyperplane, and the classification is to try to minimize to minimize trade-off of the number of misclassified points and the size of the margin. And you can also add the box constraints, right? You can add this. So here is we want to find these parallel lines, these two parallel lines, so that we minimize points on the wrong side and maximize margin of the separation. Okay, so we can formulate a bilevel model, right? So again, here your upper level is the variable is lambda, the penalty parameter, and also the margin width, W bar. So given these two parameters, you can do the SV classification to find WK, CK, and then we'll try to minimize the cross validation error. So like in the Russell problem. And similarly, we can using the change of variable to change this lower level objective into a completely convex objective. So then we can use our algorithm. So here, okay, so now how the algorithm will work. First, we will need, so you have a difference of convex. So we can first consider this difference of convex bilevel program. Right? So here, I put all these constraint x times y and the g into C. And then here, this is difference of convex function, and this is difference of convex function by our assumption. And we use epsilon. So here, if epsilon equals 0, then this is the value function. And if epsilon is positive, it means the lower level is just approximately minima. Okay, so then in order to solve this by DC algorithms, the idea is linearize the concave part. So linearize this part and this part, right? So you need one sub-differential to linearize it. So first you will, okay, so, but the value function is convex in this case, and then you.
Hello, Jane.
Yeah.
If you can wrap up in about 1 to 2 minutes, that would be.
Yes, yeah, it will
Thank
be,
you.
yeah, okay,
Thank you.
So here you take the element in the value function, right? So then and then the point is that for any, if you take epsilon positive, then the extended MFCQ always hold. Okay, so then this is how you first you take the current iteration point, you solve the lower level. Since convex, you get a global minimizer, and then you can also get the multiplier. And then you can select the element of the sub-differential, and you linearize the concave part. Okay, so everything is a convex program, so you can solve. And then this is a convergence theorem. This is the KKT point, and this is convergence theorem. In the convergence theorem, not much assumption is needed, or you don't even need to assume constraint qualification for lower level. You only need to assume the multiplier is non-empty, okay? And then either epsilon is positive or epsilon is equal to 0, but the penalty parameter is bounded, okay? And then because it's convex problem, you can use also the MPCC approach. So we compare our approach with the MPCC approach, and we find the time is much shorter. Okay, so that's end of my talk, and it's based on these two papers. Okay, thank you.
Thank you, Jane, for the nice talk. So any questions for Jane? just wait for a few
Yeah.
seconds until the question comes in. And if you have any question, please feel free to unmute yourself and ask. Okay.
Sure. I'll ask one question.
Hi.
Yes, please.
So the Mangasarian-Fromovitz constraint qualification, the standard one has these equivalences to stability, but you're using an extended Mangasarian-Fromovitz. Is there any problems with the stability of the problem if Mangasarian-Fromovitz doesn't hold?
Yeah.
But you have to use extended Mangasarian-Fromovitz?
That's a good question. Okay, so that's why we use this condition. We actually, okay, so here, okay, so see, if we use a positive epsilon, right, then we sacrifice the accuracy of the lower level solution, but the MFCQ always hold without any condition. It is when epsilon equals 0, then this does not hold. That's a problem. But I think it is not a big problem to use epsilon positive. And from our algorithm results, you see that we even tried with epsilon equals 0, although theoretically you do not have the result, right? But computation is still work. Theoretically, we can only guarantee if you take the epsilon small positive, then theoretically guarantee. But somehow, even when the epsilon equals 0, we don't have the extended Mangasarian from its constraint qualification. The calculation is still quite close, quite good. So we don't know.
Okay, thank you.
Yeah.
Thank you, Henry. Other questions? Okay. If not, let's unmute ourselves and thank Jane for the nice talk.
Thank you.
Okay, so now I'm going to stop the recording and people can feel free to talk.